Welcome to the Problems Channel Season 2, Episode 31, the episode which I titled Largest Circle on a Chessboard, because in this episode we will find the radius of a largest circle that can be drawn on a standard 8x8 chessboard in such a way that that circle passes through the black squares of the chessboard only. Before we do that, however, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the home page of this channel and in the channel's trailer section find the episode titled The Problems Channel How To. Watch that episode in its entirety, follow all the instructions that were given that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E31, we are asked to find the radius of a largest circle that can be drawn on a standard 8x8 chessboard in such a way that that circle passes through the black squares of that chessboard only. Because my experience on Quora tells me that the students of mathematics come from all sorts of countries and from all sorts of walks of life with different level of preparedness for doing mathematics. I just want to make sure that we're all on the same page and we understand well that a circle as a geometric object is very much different from a disk. And a traditional purely mathematical explanation for the difference between a circle and a disk is the following. If we place the origin of a traditional Cartesian coordinate system into the center of a circle, then the set of points in the corresponding in the parent plane that satisfies the following equation: x squared plus y squared equals r squared, where r is the distance, for example, from the origin to this point on the x-axis, is precisely what we refer to as a circle. And here the key is the exact equality when the sum of squares of the x and y coordinate of any point taken on that shape that we refer to as a circle is precisely equal to the square of the difference, to which we refer as the radius of a circle. On a disk, for example, the situation is similar, but it's subtly different. If we do the same and place the origin of a Cartesian coordinate system in the point called the center of a disk, then what will be the equation of such a disk? Well, in this case, the set of points in the parent plane that satisfies the following inequality this time: x squared plus y squared is less than or equal to r squared. See, that's the difference. Less than or equal to, precisely equal to. That's one way to give purely formal mathematical definitions of a circle and a disk. But from the standpoint of physics, we can look at it the following way. Let's say a point mass is moving along a circle. How many numbers are needed in order to completely describe the position of that point in space over time? Well, evidently only one number is needed to completely describe the position of the point on a circle in space over time at any time, and that number is the angular displacement of the point with respect to an arbitrary straight line that passes precisely through the center of that circle. See, one number. Consequently, in theoretical physics, we will say that this mechanical system possesses 1 degree of freedom. Now, if a point is roaming the innards of a disk, then the similar question: how many numbers are needed in order to completely describe the position of the point in space over time? In this case, the answer is 2 independent or 2 different numbers are needed in order to completely describe the position of a point mass that roams the innards of a disk. And what are these numbers? Well, one number is still an angular displacement of the point with respect to an arbitrarily drawn straight line through the center of that disk. Let's say this angular displacement as the angle theta. And what's the other number? The other number is the distance from the center of the disk to that point, and we can refer to that distance as r, for example, lowercase r. And to give you a somewhat practical application of these ideas where there is a difference between a circle and a disk, let's say this point, we refer to that point as uppercase R. That point roams the innards of the origin-centered unit disk. It means that this distance over here is what? The coordinate of this point is 1, 0. And in the near future, we'll evaluate the following. We'll show how to evaluate the following integral. Definite integral from 0 to pi, natural logarithm of 1 minus 2 times r times cosine of theta plus r squared d cosine d theta. You see, the argument to the logarithmic function over here may look scary, but it's not that scary if we precisely bring in the disk interpretation of what is going on over here. Recall the middle school law of cosines. What does it say? The square, here we have the following setup. Let me draw it over here. The point R, the distance R, this is the angle theta, this distance is 1, and this is the distance, let's say, rho. What is the square of this distance according to the law of cosines from middle school? Well, this is the origin. This distance over here is 1. This distance is r. So what is the square of this distance? Precisely, it's the square of the length of one side of this triangle plus the square of the length of the other side of this triangle, minus twice the product of 1 times r, the length of the sides of this triangle, times what? Precisely the cosine of the angle between them, times the cosine of the angle between them. And voila, we have our geometric interpretation of the argument of the natural logarithm, and that interpretation comes to us precisely courtesy of a disk. And for anyone interested, when the module of this real number r is less than 1, then the integral becomes 0, and if it's larger than 1, then it becomes 2 pi log r. That will be the answer. But in any way, the point that I'm trying to make over here is that there is a significant difference between a circle and a disk. And in this problem over here, we are looking precisely for a circle, not a disk. And before we deep dive into the solution of the problem S2M33, I would like to take a few minutes and explain how the eliminate and conquer problem solving approach works, because we will be solving the mathematical problem S2M33 precisely using the eliminate and conquer problem solving approach. On the one hand, the eliminate and conquer problem solving approach was popularized in Western literature by Arthur Conan Doyle through his immortal character of Sherlock Holmes, who apparently used to posit that if all the impossible has been eliminated, then whatever remains, however improbable, is the truth. On the other hand, a different but equivalent name for the eliminate and conquer problem solving approach could be the following: the method of exhaustive enumeration. And if we want to apply the method of exhaustive enumeration to the process of searching for a solution of this or that technical problem, then we should follow or try to carry out the following 3 steps. First, we should find all the possibilities for the variance of the local material, whatever that material will be. As a second step, once we lassoed in all the suspects or all the culprits, so to speak, or we think that we lassoed all the suspects, we should engage in the iterative or repetitive process of eliminating these possibilities one by one for as long as that elimination is possible. And as the third and the final step of the eliminate and conquer problem solving approach, whatever remains after all the previously delineated elimination rounds have been carried out, then that whatever may be the answer. And here is the reason why I underline the word maybe in this description of the eliminate and conquer problem solving approach. Because the eliminate and conquer problem solving approach has the following fundamental flaw. When it comes to carrying out the very first step in the application of the eliminate and conquer problem solving approach to the process of searching for a solution of this or that technical problem, this problem solving approach has very weak predictive power when it comes to doling out any sort of guarantees that the culprit or the usual suspect has been lassoed in. And for example, if we cast our net meekly, that is too narrow, then it may so happen that we simply will not scoop up the culprit or the suspect of our problem at hand. On the other hand, if we are too aggressive and we cast our net too wide, then the sheer amount of work that we need to carry out in order to engage in the second iterative or repetitive process of eliminating possibilities may be computationally prohibitive. In other words, in the first case, if we cast our net too narrow, we may come up empty at the third stage of the application of the eliminate and conquer problem solving approach to the process of solving this or that technical problem. And in the second case, if we cast our net too wide, then we simply may not have enough reasonable time to crunch through all the calculations. That is why the eliminate and conquer problem solving approach should be applied sparingly. And one more time, so that we're all on the same page, we should, when we decide to apply the eliminate and conquer problem solving approach to the process of searching for the solution of this or that technical problem, we should always be mindful of this fundamental flaw of this problem solving approach. However, sometimes in mathematics and theoretical physics and computer science, there exists this balanced situations. And what does the balanced situation mean? A balanced situation means that on the one hand, we can pretty much guarantee that we lassoed in our culprit or our usual suspect when we carried out the first step, when we find all the possibilities for the variance of the local material. And on the other hand, we can also guarantee that the amount of computational work that we need to carry out in order to eliminate certain number of possibilities is not prohibitive. It's doable, and it's doable in a reasonable in a reasonable amount of time and in a reasonable number of steps. Now that we more or less understand how the eliminate and conquer problem solving approach works in theory, let us look at a straightforward example when the application of the eliminate and conquer problem solving approach delivers fast results. In order to demonstrate how the eliminate and conquer problem solving approach may work in practice, let us consider the following classical by now problem of 27 coins. In other words, in this sample problem, we're asked to describe a way to determine with absolute certainty one fake and heavy coin amongst the set of 27 visually indistinguishable coins using pen scales and precisely 3 measurements. How do we solve this specific problem? Well, in order to solve this problem, we basically take the page from the Eliminate and Conquer problem solving approach book verbatim, lift it, and put it onto the problem. So here I erased the long and wordy description that you guys can always rewind to, copy to your paperwork, and commit it to memory. But here I left all the essential steps. So find all the possibilities. So what are all the possibilities? All the possibilities are 27 visually indistinguishable coins. This is our space of uncertainty, so to speak, amongst the 27 visually indistinguishable coins. There lurks precisely one coin that is not fair, and it is known ahead of time the quality of the weight quality of the coin is heavy. It doesn't really matter, it could be light, but let's say it's heavy for the sake of the argument. So how do we apply the eliminate and conquer problem solving approach to the process of recovering the solution of this problem? Well, first, find all the possibilities for the variance of the local material. What are all the possibilities? All the possibilities here is 27 points. We do not have any more. And we're also given one set of properly functioning fair pen scales. We're asked to do this problem in no more than 3 weighings. And how do we proceed? How do we structure, or how do we construct the keep eliminating iterative process that is the first step in the eliminate and conquer problem solving approach? Well, here 27 divides nicely into 3, right? So 9 coins, 9 coins, 9 coins, 9 coins, and 9 coins. So here we set up our elimination rounds. For example, we divide the group of 27 coins in 3 equally sized piles, 9 coins each. We take any which pile and put it onto the left pen of the pen scales. We put another 9 coins onto the right pen, and we keep the remaining 9 coins on the table. Now we consider again all the possibilities one more time, coming back to all the possibilities. What are all the possibilities in this particular partition of the coins? Well, it may so happen that the 9 coins on each side of the pen scales, on each pen of the pen scales, balance. So what does that mean? That means that 9 coins in this case that are positioned on the table, the 9 coins on the table are the suspects. What does that automatically mean? That automatically means that 9 plus 9, 19 coins have been eliminated from the consideration for containing a culprit. You see, one measurement, 18 coins eliminated, 9 coins are identified as the pool of suspects. What is the other possibility? Let's say the left pen went down, meaning the right pen went up. What does that mean? Well, we know the quality of the fake coin ahead of time. It is heavy. That means that amongst the 9 coins that sit on the left pen of the pen scale, the pen that went down, is precisely among these coins is our suspect. What does that mean? That means that all 9 coins that were in the pen that went down, went up, the right pen, and the 9 coins on the table, 9 plus 9 are 18, are no longer the suspects. So these 19 coins are eliminated. That is precisely what's happening over here. Eliminated. Keep eliminating. And what happens if, for example, the right pen goes down? Well, the situation is symmetrical. If the right pen goes down, we know the weight quality of the coin ahead of time. It is heavy. That means that the 9 coins that are sitting on the right pen, the pen that went down, contains the suspect, the fake coin, and all the coins that sit on the left pen that went up, and all the 9 coins that sit on the table are no longer the suspects. These 18 coins are eliminated. Essentially, fundamentally, what that means that once we go through all the possibilities, we eliminate 18 coins in one measurement. So once we come to the second measurement, we have a pile of what? 9 coins, no matter which side of the pen scales or the table they came from. And here, what do we have? we have essentially and fundamentally the same problem. This time, however, we partition our 9 coins into sets of what? 3, 3, and 3. These 3 coins go onto the left pan. These 3 coins, let's say, go onto the right pan. And these 3 coins go onto the table. And we repeat the experiment again. No matter what the outcome of this measurement is, if the pans balance, it means the 6 coins are eliminated these times. And the coins that are on the table, the 3 coins that are on the table, they contain the fake coin. If the left pan went down, it means that among the 3 coins on the left pan, there is a suspect. And these 3 coins on the right pan and on the table, are eliminated. And if the right pan went down, that means that the 3 coins on the left pan that went up and the 3 coins on the table are no longer the suspects. They are eliminated. So here we eliminated 18 coins. And with the second measurement, we eliminate how many? 6 coins. And that means that for the third and the final weighing, how many coins we will have, no matter what the outcome is? We will have precisely 3 coins left. And 3 coins, again, can be partitioned into what? Let's write it down over here. 3 coins can be partitioned again. 1 coin, 1 coin, 1 coin. And how do we solve this problem finally and during the third measurement? Fundamentally and essentially the same way, by using the elimination process. If let's say this coin goes on the left pan, this coin goes on the right pan, this coin goes on the table. Let's say the pans balance. That means that the coins that are on the pans are eliminated, and there is only one suspect left with absolute certainty. Bam, we know that this guy is the fake coin and it is heavy. If the left pan goes down, then the coin on the right pan and on the table are eliminated, and we know that the fake coin that is heavy is on the left pan. This guy, we point to that coin. This is the identity of this coin. And if the right pan went down, that means what? That means that the coin that was on the left pan and the coin that was on the table are what? They are eliminated from the suspect, from the pool of suspects. And with absolute certainty, the fake coin is the one that is located on the right pan. And that is how we solve this problem using the eliminate and conquer problem solving approach. One more time. Find all the possibilities, examine all the possible outcomes, and also limit ourselves to 27 points. Keep eliminating as a repetitive process during the first weighing, during the second weighing, and during the third weighing. And whatever remains, whatever the outcome is observed during the final measurement, must be it. So that final outcome will point with absolute certainty to a fake coin that is heavy. And that is how we solve this 27 coin problem using the eliminate and conquer problem solving approach. Putting the fake coins aside, we now go back to our original mathematical problem S2E31, and in order to develop a better feel for what is going on in that problem, we carry out the first round of eliminations by concentrating our attention on a standalone or single black square on a standard 8x8 chessboard. Those of our viewers who have studied the basics of the theory of sets may remember the following fact that at first comes across as quite amazing. The cardinality of the set of all the points contained in the unit line segment from 0 to 1 is actually the same as the cardinality of the set of points contained in the unit square constructed on that unit line segment. Consequently, if we ask the following question, how many circles can be constructed in such a way that they're fully contained by a single black square of a chessboard, then the answer to that question will be the following. If we agree that the boundary of a black square of a chessboard, the boundary or the border of that black square is also black or belongs to that square, then evidently it is possible to construct uncountably infinitely many circles in such a way that all these circles are fully contained within the black square of a chessboard. We can construct them here and here and here and here and here and on and on and on. And even though, if you remember our early discussion in the previous segments about the difference between a circle and a square, in this case, when we concentrate only or work only with one black square, these circles will also work when the circles become disks. In other words, the disks constructed within a single square of a board will also work in that sense. But the question that we have now is the following: what is the largest such circle that can be constructed within the black square of a chessboard in such a way that that circle is fully contained by that square? Well, since we agree that the boundary of a black square is also black or belongs to that square, then the answer to the question is the following: the center of such a black square will also play the role of the largest circle that can be constructed in such a way that that circle is fully contained within the black square. How do we locate the center of a square? Well, a square is a regular four-gon, and one way to locate the center of that polygon is to construct two perpendicular bisectors of any two distinct sides of such a polygon. For example, this side and this side. Locate the center, and then if we agree that, again, the length of the side of our black square or any square on the chessboard is 1, then we construct a circle centered at the point O, that is the center of the black square, and the one that has a radius that is equal to 1/2, like so. In other words, we inscribe a circle into a black square like so, and voila, we have a largest possible circle that is fully contained by a black square on a chessboard. And technically, if we increment or increase the radius of the circle by any strictly positive real number, epsilon usually, as it goes in real analysis, then we will step out of the boundary of a black square, and that circle will no longer be completely contained by such a square. This will not be a candidate at all, because for such a circle we'll have, evidently, in the best case scenario, we will have how many? 4. We'll have 4 arcs that do not belong to the parent black square. And on every standard 8x8 chessboard, what are the situations with the black squares and surrounding white squares? Well, here is a typical standard 8x8 chessboard. So in the best case scenario, we have how many? 1, 2, 3, 4. We have 4 white squares that surround a good candidate black square. What's the next case? The next case, for example, for this black square, how many white squares do I have around it? 1, 2, 3. 3. And then this black square is located on the border. But remember, in our problem, the solution circle, the largest circle that passes only through the black squares, has to be fully contained by this chessboard. So the circle that passes out of the boundary of a board is also not a valid solution. And in the worst case, like for example, the corner, the black square in the corner located over here, will have 2 neighboring white squares. So in either way, in this case, we will always violate the requirement that was stipulated in the problem statement, and the resulting circle will not be fully contained by the black square. And this brings us to the following interesting question. We feel now that it may be possible to construct a solution circle that is not fully contained within one black square of a chessboard, but passes through several black squares. And what points, how can the solution circle be constructed? Well, if we execute the following maneuver, let's agree that we place our favorite orthogonal XOY coordinate system in the Euclidean plane in such a way that the lower left corner of our board is located precisely at the origin of such a coordinate system, like this. The lower left corner sits at the origin of the X or Y Cartesian coordinate system. Then what kind of two independent maneuvers can we execute over here in a fruitful manner? Well, one independent maneuver could be the parallel translation of our chessboard by its linear size by 8 units of distance along the y-axis this way and this way. And the other independent maneuver will be the parallel translation of our board by its linear size, 8, along the x-axis in this direction and in that direction. If we carry out these two independent maneuvers, then what will happen? We will generate evidently the so-called unit square lattice. I'll show it, for example, here it's smaller version. So in this case, we will cover the Euclidean plane with a lattice that looks like this, and the unit square is the distance, the smallest distance, for example, 1. And in this case, what do we realize? We realize that if this problem has a non-trivial solution, then such a solution circle must do what? It must pass precisely through the nodes of such a unit square lattice, and no other possibilities exist. You see, in some sort, this is also another type of an elimination, because any circle that passes through the side of the black square, we already saw, will do what? It will either pass through the neighboring white square, which is a violation of the condition that is stipulated in the problem statement, or it will step out of the boundaries of the chessboard to begin with. This is also a violation because we are looking for a circle that is fully contained within the chessboard. As such, we now conclude that if a solution circle for this problem is possible, if it exists, then it can only pass through the integer points of our unit square lattice that we generated, as I explained before. And that means that this brings our attention to only these four vertices of a black square of a chessboard. And we will now take our elimination rounds precisely to these 4 points in the next segment. Wonderful. Our next elimination round will reduce the number of points of a black square of a chessboard, which we will have to analyze for the possibility of existence of a solution circle in our problem. That is, from the experiments that we carried out in our previous segment, it is evident what? If we consider all 4 vertices of a black square, then we already know that such a possibility has been eliminated, because we already explained that in that case, a circle that passes through all the 4 points of such a square will not satisfy the conditions that were stipulated in the problem statement. Such a circle will either step out of the boundary of the entire board, or it will run through at least one white square and thus violate the condition that was stipulated. Now, can we consider any 3 points of any 3 vertices of a square, no matter which 3 such vertices we take? Yes, we can. In some sense, 4 is a stronger condition, but through any 3 distinct points, there passes a unique circle, and that also means that such 3 points taken as a set will also be eliminated, because through such 3 points there will pass a circle, but such a circle will violate the constraints stipulated in this problem. In other words, now we only limit ourselves after 2 more elimination rounds. we limit ourselves to examining just pairs of points. And which pairs of points these would be? Well, because a square is a reasonably symmetric shape, because, for example, the set of all rigid congruence motions of a square under the operation of composition forms a group that is isomorphic to the finite dihedral group 2 times n, which is 2 times 4, or d8. It has 8 congruence motions in 8 different ways through rotations and reflections. The square can be taken into itself. That means that which pairs of vertices of such a square we consider doesn't really matter. For example, for demonstration purposes, let's concentrate on this vertex of a square. I'll designate it with A. This one I'll designate it with B. And let's say this one doesn't really matter, but I'll designate it with C. And we see that if a solution circle of this problem does exist, then it either passes through any two vertices of a black square that belong to the same side of that square, as shown over here, for example, the points A and B, or such a solution circle will pass through 2 points that belong to one and the same diagonal of that square, for example, as points A and C shown over here. Thus, we have 2 cases to analyze. The points, let me write down this pair over here, the points A and B, and the points, let's say, A and C. These are all the possibilities. So now, after all the elimination rounds that we carried out, we boil down our problem to the analysis of these 2 possible cases. Either the candidate solution circle passes through 2 vertices of a black square of a standard 8x8 chessboard that belong to one and the same side of that square, or such a candidate solution circle passes through 2 points of a black square of a chessboard that belong to one and the same diagonal of that square, or the points A and C. We will analyze these cases in their own separate segments. Very good. In this segment, we'll carry out another elimination round that covers the case when the candidate solution circle in the problem S2E31 passes through any 2 vertices of a black square that belong to one and the same side of such a square. In our case, for demonstration purposes, let us assume that these points are A, shown over here, and the vertex B, shown over here. Again, due to the symmetry of the building blocks or the squares of a chessboard and the chessboard itself, it doesn't really matter which such 2 points we pick and which other adjacent black squares we pick for analysis. For demonstration purposes, let us assume that through the vertex A over here, shown in this in the lower left corner of this square, also passes another black square over here. I'm not gonna draw it in its entirety, it doesn't matter, we understand what's going on. Another black square of with a side that is equal to the unit length. It's located somewhere over here. 1, 1, 1, 1. So here again, we apply the eliminate and conquer problem solving approach to this smaller or miniature problem one more time, and in its entirety. We identify all the possible variants of the local material, then we step through the elimination rounds. Whatever remains, however improbable, must be the truth, in the words of Sherlock Holmes and Arthur Conan Doyle. So here, let's see, we have A, B, C. Okay, let's name these guys the vertex A, B, C, D, E, and this point will be F. This is all the possible, again, when In the description of the eliminate and conquer problem solving approach, we read the very first step, identify all the possibilities of the variance of the local material. What does that mean? What is the local material in this miniature smaller problem? The variance or the local material in this case, since we have 2 points A and B, and we need to identify the third point for a unique or unique enough circle in this case, the local material becomes the vertices, the remaining vertices of an adjacent black square of a chessboard that shares the same vertex as the vertex A of this black square. And what is the variance of this local material, or what are all the possibilities for such points? Well, all the possibilities for such points are the vertex D, the vertex E, the vertex F, and the distances, all the interesting distances between these points, as we know, due to the unit square lattice, are integral distances. Let's say they're all 1. Now we engage in the repetitive or recursive, if you will, elimination rounds. Let's go this way. The point F. Can a circle pass through 3 distinct but collinear points, such as B, A, F? We already covered that case. The answer is no. If 3 distinct points are collinear, then such 3 distinct points create or generate 3 distinct line segments of finite length, for example, BA, AF, and BF, and the perpendicular bisectors to all these 3 line segments of finite length are what are parallel and in the Euclidean plane. If 2 straight lines are parallel, they never intersect, so they have no chance of designating or locating the center of the circle that will pass through these 3 points. Thus, the point F, let's say this point F, is what? Eliminated. I'll write it down with the, I'll cross this point with the red chalk. The point F is eliminated. What does that mean? That means that the only 2 suspects we have in our suspect pool are what? The vertices D and the vertices and the vertex D and the vertex E. Now, if the circle, if the candidate solution circle passes through the points B, A, and E, shown over here, these 3 vertices, this vertex, and this vertex, then what can we say about the radius of such a circle? Well, the center of such a circle will be located where? It will be located at the intersection of, let's say, the perpendicular bisector of the line segment BA and the perpendicular bisector of the line segment EA, somewhere like so, somewhere right here. It will be located here. Let's say it will be center O1. What can we say about the radius of such a circle? Well, if we draw our pictures, if we draw our diagram carefully, then we will see that such a circle, what will hold true for the radius of such a circle? This distance over here will be 1/2, and this distance 1/2. And what about this distance? Or this distance, and then this distance over here. Let's say we will erase this bad experiment and use the better one. What can be said about this distance right here? Well, this distance will be 3/2. So consequently, for the radius of this circle, what we will have? The square for this radius will be what? 1/2 squared plus 3/2 squared, and that will be what? 9, 1, 10, so that will be 10/4, and then the radius, the candidate one, will be what? Square root of 10/2. That will be 1 radius. Fine, let us analyze the case, the remaining case when the candidate solution circle passes through the points A, B, A, and D. Again, where will the center of such a circle be located? Well, the center of such a circle will be located at the intersection, again, of the perpendicular bisector of the line segment BA, let's say, and the perpendicular bisector of the line segment DA. A. So here, it will be here, and that circle will run like so. So what can we say about the radius of this circle? This will be the point O2. This will be the radius 2. What can we say about the radius of that circle, that solution circle? Well, the radius of this circle, radius 2, will evidently be what? Square root of 2 over 2. That much we understand. It's the half of the length of the diagonal of the parent square on the chessboard. 1 square plus 1 square will be 2 square root of 2, and we cut this length of this diagonal in half between two radii, square root of 10 over 2 and square root of 2 over 2. Which one we pick for the largest candidate? Evidently we pick this guy because clearly R1 is greater than R2 strictly. Why is that? Well, evidently because 10 is greater than 2, and these are all this is all for the application of the eliminate and conquer problem solving approach to the case when the solution circle, if it exists, passes through any two vertices of the parent black square that belong to one and the same side. Or this is it for this case over here for the points A and B. And in the next segment we will analyze the case when the candidate solution circle passes through the points A and C. Great, now that we analyze the possible solution circles that pass through the vertices of the parent black square of a standard 8x8 chessboard A and B that belong to the same side of that square, we will analyze the remaining case when the candidate solution circle passes through the points A and C that belong to one and the same diagonal, or the points that do not belong to one and the same side of the parent square. In this case, again, it doesn't really matter which adjacent black square we consider. For demonstration purposes, we consider this square that we used in the last segment. And again, here with the analysis of this case, what do? We apply the eliminate and conquer problem solving approach in its entirety to this scenario anew, so to speak. What is the all possible variance of the local material in this case? All possible variance of the local material in this case is again the same vertices D, E, and F that we identified in the previous segment. But in this case, we have to look at these three candidate vertices slightly different, because this time our candidate solution circle has to pass through the points C and A. In that respect, let's concentrate on the point E. What can we say about this point? Well, the point E sits on the same straight line that is defined by the points C and A, which is to say that even though the points A, C, and E are distinct, these 3 points are collinear, and we already know that under normal circumstances in the Euclidean plane, such 3 distinct collinear points cannot possibly house a circle. That means what? That means that the point E now is eliminated. This is our first elimination round. The point E is gone. So what remains? After the first round of elimination, we have 2 candidates left, the point D and the point F. And again, due to the symmetry, either point is valid to consider. If our candidate solution circle passes through the points C, A, and F, it will run this way. It will be concave in this direction. It will run this way. And if our candidate solution circle passes through the points C, A, and D, then it will be concave this way, and it will run in that direction over here. Let's say we'll consider between 2 equivalent points D and F. We'll concentrate on the point D just because we already have much of the material set up. In that case, what can we say about the radius of that circle that will run somehow this way? It will run through the points D, A, C, A, and D this way. This will be our solution circle. Let me highlight it with red maybe. It will run this way somehow. What can we say about the radius of that circle? Well, first of all, where will the center of this candidate solution circle be? The center of this candidate solution circle is located at the intersection of the perpendicular bisectors of the line segment DA. We already showed it here. Is this guy right here. And the perpendicular bisector of the line segment AC, which is the diagonal of the square. It will run this way. It will be exactly the other diagonal. And here there will be a point, let's call it 0.03. It gets a little messy, but still we see what? We see that the radius of that circle, which let's say I'll designate it with this line over here, this will be our candidate R3. What can we say about the length of the radius of that circle? Well, the length of that radius is, again, straightforward to determine. This distance will be 1/2. This distance will be 1 plus 1/2, just like in the previous case, will be 3/2. And then for R3, we will have what? The square root, again, of 1/2 squared by the Pythagorean theorem applied to this right triangle over here. From here to here, right angle, here and here. So from this triangle, right triangle, by the Pythagorean theorem, we have 1/2 squared plus 3/2 squared plus 3/2 squared. Again, square root of all this mess. And this comes down to square root of 10/4. You see, again, in this case, we have only one candidate circle because, well, technically two circles, but it is evident that the radius of the circle that will pass through the points C, A, and F will be the same as the radius of the circle shown in red over here. And that length of that radius is, again, square root of 10 over, square root of 10 over 2. Over 2 square root of 4 is 2. So square root of 10 over 2. And if we compare this case of the points A and C that belong to a diagonal with the case where points of interest belong to one and the same side, then in the previous case we had the center of the first circle over here. And what was the right triangle there? Well, the right triangle there was this one, this, and then points A and B, for example, and then the point E was here. So this could be our right triangle, this guy, this right triangle. So if we apply the Pythagorean theorem to this triangle, length 1/2, 1 plus 1/2, 3/2. This is where this formula came from, just to make sure that we all understand, from this triangle, and voila, we have our answer. Square root of 10 over 2 in the analysis, from the analysis of the first case, square root of 10 over 2 from the analysis of the second case. And what is the largest number between the two? Well, the largest number between the two is still square root of 10 over 2. This is our answer. The problem is solved, and in the next segment I will show you all the possible circles that will satisfy this condition, and in some sense this will be all the solution circles for the mathematical problem S2M33. Now that we solved the mathematical problem S2M33 in principle, let us analyze that solution a little bit. Due to the nature of the question that was posed in that problem, the maximal length of the radius of a circle so and so, it is evident that the actual solution or the answer to that problem is unique. In other words, the length of the largest circle that can be drawn on a standard 8x8 chessboard in such a way that that circle is fully contained within that board, and that circle passes only through the black squares of that board, is equal to square root of 10 over 2, as we demonstrated in the previous several segments. However, the actual solution circles that satisfy that requirement, the number of such circles, is not unique. It's not one circle, but in this case, it should be evident that it is possible to construct precisely 8 such solution circles. I showed it on your lower right side of your screen over here. 8 solution circles such that they have the radius that is equal to square root of 10 over 2. And each such circle is precisely contained within the parent 8 by 8 standard chessboard and passes only through the black squares of that board. Now let us agree that the solution square in this case will be the smallest square on the parent chessboard that contains all the black squares whose centers play the role of the centers of the solution circles. And that smallest circle, or smallest square, I'm sorry, or the solution circle is shown over here in red. You can see it over here, and I gave it a little bit of a cross hatch in red. And to be perfectly clear and explicit, that smallest solution square sits precisely in the center of the parent square. And let's say if we take the standard naming of the columns and the rows of a chessboard, then this solution square will be delineated by the following squares: C3 on the lower left, C6 on the upper left, and F3 on the lower right, and F6 on the upper right. I depicted that square over here on that side, and apparently I forgot to put another dash over here. This is the solution square. And what does it mean? It means that that square is the smallest square that contains all the black squares whose centers play the role of the centers of the solution circles. Let's count these black squares over here. 1, 2, 3, 4, 5, 6, 7, 8. And in red, with the red dot shown over here, I depicted the center of every black square, I'm sorry, that is contained within the solution square, or the smallest square that contains all the squares whose centers house the solution circles. And each such solution circle can be constructed which way? Well, perhaps the most straightforward way is just to capitalize on the points that we already have, the so-called nodes of the unit square lattice, and just construct two perpendicular diagonals of such a square, locate the center, and then from that center, for example, from this point over here, we do what? Well, for this particular case, we walk one half of the units of distance, let's say east, and then we climb north by 3 halves, 3 over 2 units of distance to this point, and voila, we have a radius, and we transcribe a circle that way. That circle is fully contained within the parent chessboard, and it passes through black squares only, as shown over here. And we can construct 8 more such circles. I constructed another circle for you for demonstration purposes over here. Again, in this case, we construct 2 diagonals of a square, that one that runs that way, the other one that runs this way. The intersection of the diagonals of that square locates the center of the solution circle. And once we have that center located, again, for example, we walk 1/2 of units of distance, let's say west, then we climb 3/2 of units of distance north. We come to this point, we open up the compass to that distance, and we transcribe a circle. In other words, this is the solution circle that is fully contained by the parent board and passes through, let's count how many: 1, 2, 3, 4, 5, 6, 7, 8 black squares only, and nowhere does that solution circle passes through not black or white circle, as shown over here. Again, just to make sure that we're all on the same page and we understand how many solution circles on a standard 8 by 8 chessboard exist. These solution circles are located in the centers of 8 black squares that are themselves positioned within the following square delineated on the standard board with the standard naming convention as follows. the lower left square is C3, the upper left corner is C6, the lower right corner is F3, and the upper right corner is F6. These two bands, this way and that way, delineate the smallest, or delineate the solution square, or the smallest square that houses all the black squares whose centers play the role of the centers of the solution circles. The problem is solved. Now we can see that we can step back a little bit and observe what our solution square, or the smallest square that houses all the centers of the solution circles, can also be flipped which way? Well, we can flip it from black squares into white squares. The same way the centers will go here, here, and how many such squares we will have? 1, 2, 3, 4, 5, 6, and 7, and 8. Again, similar circles that are fully contained within the parent 8x8 standard chessboard and pass through white squares only. This is it for the problem S2, for the mathematical problem S2M33, and we will move on to the new challenge next. In order to showcase the awesome tactical power of the eliminate and conquer problem solving approach, we will switch gears a little bit and step away from this strange but beautiful chessboard geometry and step up close to the elementary theory of numbers, because in the next challenge, the mathematical problem S2M34, precisely using the eliminate and conquer problem solving approach, we're asked to find two whole positive numbers n and m such that first, their least common multiple, or LCM, least common multiple of these two numbers, is equal to 84, a magic number, but still 84, it is what it is, and one of these numbers is by 5 larger than the other. Let's say the difference between the second number and the first is precisely 5. And in order to make sure that we're all on the same page in terms of understanding what needs to be done with this problem. Yes, this problem can be solved in a number of different ways, and some such ways can be shorter, more elegant, more simpler, whatever that means. However, the objective of this challenge, the point of trying to solve this problem, is not to find a simplest or the most elegant, the shortest solution in some sense, but the objective of taking on this challenge is precisely to find a way to apply the problem-solving approach that we're studying right now. In other words, the objective of solving the mathematical problem S2M34 is to precisely apply the eliminate and conquer problem-solving approach to the process of developing or discovering the solution of the problem S2M34. In other words, if you want to understand how to apply the eliminate and conquer problem solving approach to a different type of problem, instead of geometry, we step up to elementary theory of numbers. Here we suggest that you play with the data that is given, try to find all the possible variances of the local material, step through these choices, start eliminating. This choice is eliminated because of that choice is eliminated because of this, and so on. Whatever remains must be the proverbial truth, and so on. Play with this approach several times until you generate a correct solution to this problem. We want to hear from you what the results are. Meanwhile, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the mathematical problem S2M34.